So how do we actually apply the things we learn? Okay, we're going to talk about the reversible isothermal expansion for ideal gas. How to calculate all these variables. When I say variables, including your delta U, delta H, Q, and W. These are the 4 variables you will always need to calculate for the first law of thermodynamics. If today we have P and V for your ideal gas under a isothermal condition, then you can actually plot out this isotherm. You perform the experiment at constant temperature. Assuming we start from P1 and then we end up with P2, but temperature remains constant through the whole process. A system that's going to do some expansion. So you have a P system, and then there's actually the external P. Is isothermal, that means actually the heat from your surrounding can goes into your system. So everybody understand what system we have now? We have a piston inside of the gas. So the heat from the surrounding can go to your system. And once the system get the heat, it's going to expand to do the work to your surrounding. The setup is we have ideal gas. And then we have isothermal condition. That means actually T is constant. So we want to calculate the delta U, delta H, Q, and W. Your U, your H is only a function of temperature. So right now you're under constant temperature. Your delta H and delta U will equals to 0. But this is only true when you have ideal gas. So now we actually just need to know how do we calculate Q, how do we calculate W. Calculate the work is actually easier than calculate the Q. Okay, so you will always have to start from calculate the work. We know dW is equals to negative P external dV. Because today you have reversible process, then you can just switch the P external with your P system. So this is only true when you have a reversible process. And then because you have ideal gas, then you can actually rewrite the first term because PV equals to RT. So your P is equals to RT over V. So I'm going to switch this one as RT over V dV. And this is only possible when you have ideal gas. And also the system we have right now is actually an isothermal condition. Right? That means actually your T is a constant. Therefore, you can actually rewrite this one, negative RT, and then you can put your dV, V together. So you can actually group those two in the constant term. So once you have this, then you can calculate your delta W is simply the summation of your dW, which is going to equals to negative RT summation dV over V. And of course, once you do this, you know your delta W will simply equals to negative RT natural log V2 over V1. Just in case that you are not so familiar with. So summation 1 over x dx is going to equal to natural log x. So the work is negative RT natural log V2 over V1. Okay, if I were you, I wouldn't actually memorize this at all. Because in order to get to these answers, you also need to memorize. It has to be under a reversible ideal gas under constant temperature. Then the work is going to relate it to the V through this equation. The things you should actually really know is actually starting from here. Okay, and then based on the specific condition you have, just write step by step so you won't confuse yourself and make sure that you can actually calculate things properly. So once you know your delta W, because delta U is delta Q plus delta W, because your delta U is 0, right? So you know your delta Q will simply equals to negative delta W. In this case, will equals to RT natural log V2 over V1. So the important thing for this example is that, what does it mean? So here you know if you have ideal gas if under constant temperature for a reversible process. So if you look back to these things, V1, V2, you are doing this expansion work. Your Q and W, the absolute value of these two, they're actually the same, but just opposite sign. It means it's actually your system is going to absorb all the heat from your surrounding. And then all the heat was being used to do the work so that your internal energy of the system doesn't change because your du is 0. The analogy of this one is like this. Assuming you have a very wealthy parents. Every morning, they put $10,000 in your pocket. So during your days, you can actually spend all those monies, okay, to do whatever things you want to do. Maybe actually, invite your significant other to a movie, buy them a dinner or lunch. But no matter what you do, it doesn't actually consume any your energy. So your internal energy still stay a constant because all you do is actually use the money you got from your parents to do the things that you want. So your internal energy doesn't really change. So let's the same analogy here. If you are ideal gas, if you have isothermal conditions, you can always take all the resource from your surrounding and do whatever you want. But your internal energy won't be actually affected. Okay, that's why your delta U, your delta H equals to 0. So this is the first example we want to go through. Second example, we still have ideal gas. Still want to calculate these 4 variables. But right now we are under reversible adiabatic expansion. Okay, so we are going to still do the same thing like here. The only difference is that right now I actually enclose my whole system inside an insulator so that there's actually no heat allowed to go into my system. So how do you actually solve this? Here, because we know we have adiabatic conditions, right? That means actually your delta Q is going to equals to 0. Then, okay, we have delta U, delta H, and the delta W need to calculate. Let me write the delta H on the other side. Because U equals to Q plus W. Okay, right now your delta Q is 0. Therefore, you know your delta U is going to equal to your delta W. Delta H is actually not kind of way to calculate. Okay, so how do you calculate these things? The answer is actually to get back to the most general equations we have. Okay, which is, okay, du is cv dt plus, a big bracket times dv. And the second one is actually dh is cp dt plus another bracket, dp. So if you look at these two, as we mentioned previously, the first term, that's your heat capacity times temperature. The second term, this P, we know is actually the internal pressure, right? Internal pressure is actually things that only non-ideal gas have. Okay, so if you have ideal gas, this goes to 0. The same thing happened to your DH. Okay, the second term over here, the V term is actually the excluded volume, right? If you have ideal gas, this term goes to 0. So with that being said, you know, if you have ideal gas, if you want to calculate your du or your dH, it will simply become CVDT or CPDT. Okay, the things that you need to figure out is actually what is the temperature change based on the given conditions. So the things you should have in mind right now is actually, you know, your delta U will be just CV delta T. Your delta H will be just CP delta T. Okay? And this is only true when you have ideal gas. Now the key thing is actually how do you know the delta T? How do you solve the delta T? Okay, so far what you know is your delta U is going to equals to your delta W. And then we know for your delta U can be calculated from or CV dt. And then for your work, we know it's actually negative P external dV under a reversible process. You know this can be written as negative P dV. You also know that we have ideal gas. We can write this as T over V dV. So here to here is ideal gas. In this case, you need to actually have a good sense about what is constant. Okay, is temperature constant here? It's not, right? Temperature will only be constant when you see the keyword isothermal appear in your question. Here, even I write T over V, let T is not constant. What you do is actually, okay, let me rewrite these two together. So CV dt is going to equals to negative RT over V dV. You need to put the T together with your dt, V together with your dV. So when you do that, you have dt over T, R over CV, dV over V. The R over CV, this is a constant. So when you integrate on both sides, finally you get the answer T2 over T1 is going to equals to V2 over V1, negative R over CV. After you do this expansion under adiabatic conditions, the final temperature T2 is actually related to your initial temperature T1 through a volume, and it actually has a volume dependence, yes. Or V2 over V1, yes. Okay, that means actually if you expand a lot, okay, that means actually do a lot of work to your surrounding, okay, then the temperature of your system is going to decrease more. Okay, so this is actually what this equation means. Okay. With that being said, this equation actually tells you if you know what is the final volume. Okay, if you know your V2, you know your V1, and then if you know your T1, then you can actually calculate your T2, right? Since you can calculate your T2, then you can actually calculate your delta T, right? Once you know your delta T, then put it back to here, then you can actually calculate your delta U and delta H for the reversible adiabatic expansion. And then because delta U equals delta W, you will also know your delta W. For us in the beginning, we know it's adiabatic, the Q equals to 0, then you can solve all four variables. The analogy of this will be, if today your parent says, okay, I disown you, that means actually he is not going to put $10,000 in your pocket in every morning. But still, you want to actually hang out with your girlfriend or boyfriend. Then what do? You don't eat the breakfast. You don't eat your lunch. You don't eat your dinners. So you can just save some money to bring your significant hat to the movie or to a nice meal. So in that case, you can consume all you have, okay, to do the work. Because you actually don't feel so much your own energy out, then your temperature gets lower. So the very last one is actually the irreversible adiabatic expansion and compression. If you plot out the PV, you actually cannot plot PV anymore, right? Because right now you don't have a reversible process. Originally, we write the dW equals to negative P external dV. But this is actually not possible anymore because right now you don't have a reversible process. Therefore, you cannot actually plot out the PV plot. All you can plot out is actually P external V. You're still going from state 1 to state 2, P1, P2, V1, and V2. For the irreversible process, what it really means is actually I have a sudden jump of my P. I actually always stay at constant P2. Okay, so that will actually make it become an irreversible step. So you know the pressure is always P2, right? So the work you do will be just this. Yeah, even though you cannot write negative P dV, but you can write negative P2 because P2 is actually external dV. Okay, so you know you can calculate your dW. Adiabatic, so you know your Q is going to equal to 0. du, dq plus dw. dq is 0. So again, you can still calculate your du equals to your dw. Of course, again, you can calculate this through Cv dt. And then you do the same thing for your dH is Cp dt. But here you can see that the information you need is still dt, right? So you still need to calculate what's the dt.